So thanks again for the invitation. It's really a nice workshop. So amazing venue and amazing speakers, amazing audience. So thanks again for organizing this workshop. Today I'll be talking about minimax optimization problems. This is joint work with Gaussian Lagal, who was a postdoctoral associate with me at Rutgers, who recently moved into France as a faculty, and also joint work with Serhat Aybat, who's at Penn State and who's a long-time collaborator of mine. So I'll be in the stochastic setting today. So it means that for the gradients, you will have stochastic estimates rather than exact evaluations. And I'll be interested in high probability guarantees. That means that I want to certify that you can find an approximate solution with high probability. So what's the min-max optimization? Well, I think for optimizers, we see such problems very frequently in our daily life. Essentially, you have two variables. You are trying to minimize over x and maximize over y. And these variables are linked together through a linking function, or also called the coupling function called phi. So such problems obviously arise frequently. For example, if you are doing constraint minimization, right? If you write down the Lagrangian, you will naturally find yourself in the primal-dual setup like this. For general problems, the functions here can be non-convex, non-concave, so it can be very general. Today, I will start with the simplest setting where things look nice and convex, and then towards the end of the talk, I will cover the more general case when things can be non-convex. Okay? So for starters, let's say that we have Lipschitz gradients, so meaning that you have a coupling function that admits kind of smooth. That's smooth in the sense that the gradients are Lipschitz. Here, because we are not in the unconstrained minimization setting, there may be multiple Lipschitz constants. So you can have a Lipschitz constant in the primal domain. You can have a Lipschitz constant in the dual domain, right? And you could also have things like LXY, LYX, that's telling you how your gradient is sort of changing if you were to perturb gradients in both directions, right? And in terms of the first problem we are looking at, we are assuming that you have f and g that are like your penalty functions that are strongly convex, and they can be non-smooth because we are going to have prox terms on them. But this is a nice problem in the sense that it's strongly convex in x and strongly concave in y, and we want to maximize in y and minimize in x. And thanks to Adrian, who covered Lipschitz functions and strongly convex functions, I don't need to define them. And the goal is to find a saddle point in this setting. And in terms of applications, beyond constraint optimization, you can always think about game theory as a game theoretical applications. For example, as a player, think of two-player games. Player X is trying to minimize some cost function, and player Y is the opponent. Maybe the player Y is trying to trick you and then maximize the cost. Right? So you will be in this kind of setting. And also in machine learning, we see a surge of applications of min-max problems. So for example, one application would be distribution robust optimization. Let's say if you are learning a statistical model, the classic setup is you go and minimize the loss function, right? But what if you want to be robust against certain perturbations or deviations in the input data? Then you would just take your dual domain Y to be a set of probability distributions. You define a robust loss that tells you the worst case situation if the input data would be perturbed. And then if you were to minimize this robust loss, then essentially you would be training models in a way that they become more robust to changes in the input data distribution. So I will give you more concrete examples of this, where you will see the exact functions. But there are many other applications, like, for example, if you want to do sort of fair classification, if you want to do, for example, we talked about generative models. So if you're trying to train GANs, for example, you would be solving these kind of problems. Right. So we have been working on a few different algorithms, and I just wanted to tell you a little bit about some algorithms we have been working on and then connect with the literature. So this algorithm, we have sort of been studying, we have studied it back in 2021. It's called stochastic accelerated primal-dual algorithm. So it's actually a very simple method. It's actually, what it is doing is that you are doing proximal gradient descent in X and proximal gradient ascent in Y. And it has a momentum in it, meaning that in the dual variable, you do some sort of momentum averaging. And it is using stochastic gradients in the sense that you have an oracle at every step. Instead of the actual gradients, you use noisy ones, right? Actually, it's an extension of the Chambol-Poc algorithm to non-bilinear problems. So when the coupling function is not bilinear, this algorithm is still applicable. Okay? So, and it's an alternative algorithm in the sense that the variables x and y are not updated, simultaneously. They are updated in a sort of an alternating fashion. So, back in the day, a few years ago, we had for this algorithm, we had some nice convergence guarantees in expectation. What I mean by that is that you run your algorithm, let's say you have a performance metric. Let's say you are trying to control distance to the settle point. And in expectation, you can say that I'll be epsilon close to a settle point. In expectation here means an average over the algorithm runs, right? While this is a great result, if something is good on average, it doesn't mean that it's always good, right? So if you go to a restaurant that's good on average, in some days you may have really bad food, right? So if you have high probability guarantees, then you can control the bad events, tail events better. So the idea was, okay, this algorithm is almost optimal for strongly convex, strongly concave problems. Can we extend it to to get like stronger guarantees in high probability? And it turns out that the answer is yes. So that's the purpose of the first part of the talk. And then we will see that same ideas will be extending to general non-convex, to much more general non-convex problems. So once you solve a problem that's in a special case, you can always try to take advantage of it. So just wanted to tell you how this algorithm works. Essentially, when you have an algorithm, as Adrian mentioned, there are some conditions for you to satisfy, otherwise things will blow up, right? So we try to, let's say, for your step size, for gradient descent, right? If step size is very large, you will blow up, right? So, for example, for gradient descent, if your step size is larger than 2 over L, where L is the Lipschitz constant, you will blow up, right? So here you have lots of constants, Lipschitz constants, strong convexity constants, etc. So we wrote down the most generic set of inequalities such that the algorithm will converge for this algorithm, right? You get a matrix inequality. If this is satisfied, then things will converge. And if this inequality is satisfied, then you get some sort of we can show that there's some sort of generic convergence result that we can show. It's a bit like if this matrix inequality is satisfied, you will get a convergence rate rho, right? It's sort of like in Adrian's talk, where you have a matrix inequality. If it is feasible, then you will get the rate that you want, okay? And one thing nice about this is that we can find solutions almost explicitly in this case. So we are lucky for this algorithm, we can figure out what step sizes give you the best behavior type of thing. And it turns out that you can get the accelerated rate. So your results have two kind of flavor. The first type of terms tell you how fast you forget your initial conditions. That's called the bias term, right? So let's say you had an initial error at initialization, it decays over time, right? So this part will tell you how fast you forget that. Right? And this kappa here is telling you that you have an accelerated sort of rate. In unconstrained optimization, kappa is bad, right? But for min-max problem, kappa is the best thing you can get. So it's a bit different. Okay. So kappa is just the ratio of the Lipschitz constant to the strong convexity constant. And then this is the variance term. It's coming from the noise. And remember that noise is persistent. So you cannot kill it easily. So meaning that if you use constant step size, for example, if you use primal step size tau, use step size sigma, you are not going to converge, but you are going to converge to a neighborhood of the solution. And that's going to be, this is called the variance part of the bound, which is going to be sort of always there, right? So you have the bias, you have the variance, and to get the best parameters, you should have the right trade-offs. Right? For example, imagine that you have a tiny step size. Because your step size is tiny, you are killing the noise, because step size scales the gradient noise, but it will take you forever to get there. So your bias will decay very slowly. At the end, you will have a nice result, but it may not be the best thing to do, right? So it turns out you have to balance these effects. And yeah. So normally you would have things like summation 1 plus rho square, etc. But here we put a bound on it. So normally here, instead of 1 over 1 minus rho, you would have things like there's sum up to n. But I can say that n is appearing here, and this is a bound that's tight for large n, if you wish. Yes, the reason for... Right. Yes, but it doesn't matter for complexity reasons. So for example, let's say you take a strongly convex function. I can use a decaying step size to get some complexity, right? It turns out that if you get just a small constant step size, you get the same complexity. Because at the end of the game, you want to compute a, so here we are in the constant step size regime, but turns out that you can get optimal complexity even in this setting. Right, so again, I mean, going back to, I think, Tom's question, how can you design parameters to get the best trade-offs? It turns out that we can do this explicitly for this class of algorithms. So we can write down, okay, choose your step size, momentum, blah, blah, this way, then you get the best complexity for this class of algorithms. Right, and so the question is like, how do we analyze such things, okay, so that we can hope to extend them to high probability sort of settings? So I want to give you intuition about stochastic gradient descent, whose proof is just 3 lines, okay? How do we analyze stochastic gradient for a strongly convex function? Well, you just say, okay, let's say that delta is my noise part. Okay, I have a stochastic gradient, I have a step size of gamma. I'm just gonna look at the distance square, how things decay. And what happens is that in your bounds, you will have 3 terms. The first term will be noise independent. It doesn't have noise in it. It is about how fast the underlying deterministic algorithm is converging. It's as if like you sort of totally isolated the noise, right? And then the noise is interacting with the iterates, because there's a dot product, and there's the norm square of the noise. So, well, norm square is just, you can bound it by the variance, because noise is centered, we can bound its moments. And the nice thing is that you have something that's null in expectation, which you can cancel out. And then if you do this, if you do unroll this sort of expectation, you are going to have some sort of decay and plus some sort of a constant. The thing is that that constant will depend on your step size. And there'll be a sort of trade-off between these 2 terms. But this is how you analyze, stochastic gradient. So for the min-max setting, it's actually almost the same. So you have something that sort of deterministic term that bounds your performance. And then it turns out that that deterministic term will be controlled. If you have a matrix inequality holding, that means that your Lyapunov function is contracting. And then there's a deterministic part that you can control, and there'll be some noisy parts that you have to somehow kill by taking expectations. I mean, there's a bit of a challenge because when you use prox terms, prox is making things a bit more complicated. But at the end of the game, you have some sort of terms that are null in expectation, and you have certain terms that can be controlled by your step size. And with this kind of logic, if you really choose the parameters in an optimal way to do the trade-off of these 2 sums, it turns out that you can get almost optimal methods. So for example, what are some lower bounds? Well, the bias term will have some sort of decay with the condition number, right? And then there's the asymptotic variance that you have to worry about because you are converging to a neighborhood. And in the literature, there have been really nice methods. There are some VI methods, basically variation inequalities, which is powerful, but they would treat the primal and dual step size to be the same, typically, if you want to apply a VI method to solve a min-max problem. It doesn't matter, but let's say I'm saying if you use the sign gradient map, for example, if you as an operator, if you use, let's say, as an operator, if you use, I would say the existing VI results we were able to find was working mostly with the global Lipschitz constants, right? So for example, you have LXX, LXY, LYY. The ones that we were able to find in the literature, they were kind of working with, let's say, L and mu, which is like the worst case scenario. It's not a bad thing necessarily, but because we kind of sort of look into all the blocks, we can have a small improvement in the sense that instead of going with the worst case constant, we can have a bit of more resolution. But at the end of the game, this problem is not too complicated. It's a strongly convex, strongly concave problem. And for example, here we have persistent noise. For example, if you would have finite sum problems, you could kill the noise. For example, I think Yura had some papers about variance reduction. So if your problem is a finite sum problem, there are more things that you can do. But in any case, when we went to the more general, high probability setting, we weren't able to find too many high probability results. So most of the results that we are aware of wouldn't have this like accelerated scaling with kappa dependency in terms of like high probability results. And in terms of the VI results, I think if you scale the operator, you may be able to capture a bit more structure. But the ones that we know were not really taking, because like exploiting the structure, the ones that were on the literature. And why is this a big deal? So for example, if you want to do, a lot of times the primal and dual problems may have different structure. For example, let's say you have n data points and maybe in dimension d, right? So the Lipschitz constants will be kind of scaling with n and d, and they can be very different. So something that can sort of capture this sort of block structure actually can help us in some settings. Right, so, but of course, VI problems can solve different problems. So VI algorithms are also very interesting. For example, there are some VI inequalities that wouldn't be a min-max problem, right? So, right. So, in terms of a catch, I would say a weakness maybe. We had to assume some sort of light tail noise. So technically, you can have heavy tail noise. You can have like let's say more general noise. But here, to get the result, we had to assume that your tails are sub-Gaussian, meaning that essentially you have some sort of sub-Gaussian-like decay of the gradient errors. And the way to motivate this is that, let's say, if you are doing batching of data points, right? Essentially, you could have a central limit theorem type of setting where the averaging can help you to get Gaussian-like behavior. But it may not be holding in some applications. For example, in deep learning, it may not be holding in some settings. Right, but let's say for high probability results, this is like a common assumption, I would say, in the literature. Right, so what we can say is that for very generic set of parameters, let's say you want to get high probability performance. Another thing I should say is that here we can handle the prox terms because of the prox gradient nature. That also we haven't seen in the literature anything that can handle prox with high probability guarantees. If you know any references, I mean, please let me know. We weren't able to find any. So here, basically, we have a control over the quantiles, meaning that, let's say, if you want a probability P, if you want your result holding with probability P, then essentially we have a formula that tells you like how you can bound the quantile as a function of the number of steps and number of, so we have made everything explicit in the paper. And in terms of the sort of, if you really go and optimize the choice of the parameters, you get a complexity that looks a bit complicated here. Maybe it's a bit hard to parse, but the main idea is that we have some complexity that sort of gives you exact dependence to Bloch-Lipschitz constants, and it is accelerated because you have like sort of kappa dependency, and then you have the right log dependency, and it turns out that this is tight, meaning that for a quadratic problem, we can analyze everything explicitly. So we can do exact computations for a quadratic problem. So that means that these bounds, at least for this algorithm, cannot be improved. So what was the main idea? The main idea is that, let's say, the analysis that I mentioned for SGD, essentially it doesn't hold in high probability, right? So when you look at the dot products, it's not going to be 0 with high probability, right? So, but there's something nice happening here. So you have a contracted Lyapunov function, right? And let's say you have some error terms, but these error terms, let's say, if things are sub-Gaussian, these error terms will be easier to control. So in particular, we had to come up with a concentration inequality that says that, for example, if you're sub-Gaussian, we can control the moment-generating function. If you are sub-exponential, if the errors are sub-Gaussian, the error squares are sub-exponential. So for these kind of distributions, we can control their moment-generating function. And we had to come up with some sort of concentration inequality because the existing ones weren't applying directly to our case. And essentially, if you have some sort of recursion in SGD, right, you can have concentration. But for these accelerated methods, the problem is that we don't know the Lyapunov function. So let's say for Nesterov, it took years to figure out the right Lyapunov function for unconstrained minimization, right? Because when Nesterov wrote back in 1983, he didn't write the Lyapunov function. So you can figure out the Lyapunov function yourself, by looking at the paper. But for the minimax problems, it's not clear because these methods are not monotonic. So you need to find construct some sort of Lyapunov function. And here it turns out that after a lot of trial and errors, there's a fancy Lyapunov function, and by just applying this kind of concentration inequality, essentially everything builds on this kind of recursion. It's like a sort of martingale type of result. If you have some contraction plus some error, you can control the moment-generating function, right? And if I want to illustrate some results, basically, let's say you choose two parameters. Let's say rho here is like your momentum parameter. One of them actually starts a bit slow, but it converges to a nice neighborhood. And the other one is very fast, but then it will stabilize. Because maybe the step size is too large. In the beginning, you are having some fast progress, but eventually, your error is too big. The error accumulated. For this class, actually, because we can sort of optimize the step size, for example, the yellow one will have better concentration. So basically, we can have basically we can have good performance. The only thing is that choosing these optimal parameters would require the knowledge of the Lipschitz constants and strong convexity constant, which we don't know. So we need to run some sort of like estimation going on to sort of do this. And in terms of like the distribution robust optimization kind of problems, for example, here we are doing logistic regression, and then essentially you are trying to sort of solve this robust learning problem. And again, for this problem, the parameters that we have gives you the right sort of histogram. So essentially, we are controlling the histogram and the high probability type of errors. So Then we were like, okay, this was for the strongly convex case, so can we do something interesting in the non-convex setting? So here, the assumption is that in the x variable, you can be non-convex. Okay, so now we can be non-convex. For the y variable, let's assume some sort of PL property, which is a relaxation of strong concavity in this setting. So for example, if you look at this function, it's not concave, but it has some sort of growth condition, right? So again, when we look at the literature, when things are strongly convex, there are really nice papers. For example, Radu and Axel has this paper about alternating methods with a good complexity. There are some other papers, and these papers are important because they say these gradient descent ascent methods are very frequently used in machine learning because they are single loop and easy to implement. So a lot of times there's a big difference between practice and the theory, right? But for the PL setting, there are not too many papers actually. The only one that I know is by Yang and from Niao's group that had recently a complexity of epsilon to the 4 type of complexity for the smoothed alternating GDA method developed by Zhang and from Tom's group a few years ago, right? The question, if you use variance reduction, maybe you could also improve these methods a bit. But the question was, there doesn't seem to be sort of any kind of high probability guarantees for non-convex problems, right? For example, when you look at the monotone VI literature, typically they wouldn't apply to non-convex problems, right? They would apply to convex problems. And for non-monotone VIs, so we looked hard into sort of seeing if there's any high probability guarantees. There's really interesting work about, for example, non-monotone VI type of conditions. I think Steve has a recent paper. There are different conditions, but there's no high probability guarantee that we could find at this point. So the guarantees are always in expectation. There's only one paper that I could find with Gorbunov and Sadiev who looks into star co-coercivity. It's like a condition that can hold for some non-convex problems. But unfortunately, it doesn't apply to the NCPL setting because what happens is that this class can allow some non-convexity, but around the solution, you need convexity. So we couldn't find any sort of result on this. And so what we could do was, it turns out that to get high probability guarantees, you don't have to pay too much. So you have to pay already epsilon to the 4. And if you just pay a little bit more on epsilon square, it turns out that you can get high probability guarantees. Okay? So basically, by just having a bit of more complexity, which is, I would say, mild compared to this one, you could have high probability guarantees. Okay? And how did we do it? Or maybe let me tell you the method first. So the method is, the idea is like a, inexact proximal point method, where you say, let me regularize the primal variable and work with that one, because if you regularize enough, right, this function will be strongly convex in X, which will have some nice properties, right? And then the parameter B tells you how you are updating your proximal centers, how fast you're updating them. So, and this smoothing is a genius idea because let's say a lot of times you can have oscillations when you run this minimax method. So the smoothing makes them sort of avoid some of the oscillations. And I think I will just wrap up in a few minutes. So luckily for this class of problems, there are Lyapunov functions available. We don't have to search for it by these papers. The problem was that we weren't able to use concentration results on the existing Lyapunov descent results. So somehow we couldn't make them work in high probability. So essentially, it turns out that we have a new sort of approximate descent property. If you choose the parameters in a particular way, it turns out that you can have some sort of Lyapunov descent, which looks like the previous inequality I presented. Remember, there's some sort of descent, and then there's the error terms, that I had. It things look more complicated, but it's the same idea. We had to sort of extend our concentration inequality to be able to apply the results. But at the end, if you have the right descent and if you have the right concentration, then you can show that essentially your average of the gradients will be controlled. And it turns out that if you choose the right step size, you don't have to pay too much for this. So if I want to summarize, basically for stochastic problems, it looks like there are not too many high probability guarantees. For strongly convex problems, we had some high probability results. In the paper, we also look into some risk measures. Like, for example, how does the risk CVAR and so forth, EVAR, evolves, for the iterates. But I didn't present it today. And then the same idea actually works for the non-convex PL problems. And I think some of the concentration inequalities can be used for other algorithms. So for example, the same concentration inequality can be used to analyze things like alternating GDA or SGD and so forth. So overall, thanks so much for listening, and let me know if you have questions.